Hi, amazing AP Physics students. In this video, I'll go through all the even numbers of the multiple choice progress check part A. So stay with me, please. I'll begin with question 2. You have planet X and planet Y. These are the parameters of these two planets, and the satellite is located at the same distance r from the surface of the planet. So the question is, how does the gravitational field on planet X at the surface of planet X compare with the gravitational field at the surface of planet Y? So the answer is B, and you have to be careful not to choose C here because it can be misleading. So the gravitational law for Gx would be gravitational constant G, big G, times the mass of the planet divided by r squared. And for the planet Y, it would be 3 times m multiplied by gravitational constant G divided by 9r squared. Therefore, it would be 1/3, right? 1/3 of Gx. But you need to answer what is Gx, not what Gy, right? So this what is confusing, I think, would be B and C. So make sure you answer in terms of Gx. So Gx equals 3 multiplied by Gy, or Gy is 1/3 of Gx. I hope it makes sense. Question 4, you have a planet, you have a moon, and you have the radius r. So the question is, the moon has a mass of 1 to 10^22 kilograms, and gravitational field strength at the distance r from the planet is 0.001 Newton per kilogram. What's the gravitational force exerted on the moon while it is in orbit around the planet? So to solve this problem, you have to multiply the mass by the G. So the mass is 10 to the 22nd power multiplied by the G, which is 10 to the -3rd. So this number would be easier to write in 10 to the -3rd format, because then you can just subtract these two numbers, 22 minus 3. So that would be the answer, 10 to the +19th power of newtons. The answer is B. So problem number 6, you have 2 containers of mass m, distance d, and then those same containers have different mass of water in them. So the question is, what's the new gravitational force exerted on one container by the other? The answer is 3/4 F original force, and you can do it by just writing this equation and substituting the new masses, and you can find that it's 0.75 of the original force, which is this equation right here. So the question is about experimentally determining gravitational and inertial masses. So you should know that gravitational mass can be just measured with the spring scale. So that's enough. You have the spring scale, you can measure the gravitational mass. For the inertial mass, you have to know the applied force, and you're supposed to know it here, and then the acceleration, right? To measure the acceleration, it's enough to have a meter stick and a timer. So using kinematic equation, you can measure the acceleration if you can measure the distance and the time. Okay, so that is sufficient to answer this question. So the other devices are not necessary to answer this question. For number 10, the student analyzes the motion of a planet as it orbits a star in a deep space. The orbit of the planet is considered as stable, does not change over time. The student claims only experimentally measurable external force exerted on the planet is the force due to gravity from the star. The student's claim supported by evidence. What reasoning either supports the student's claim? So this A and B might be confusing. So B says yes, the only external force exerted on the planet is the force due to gravity from the star, which is incorrect. So no matter how far massive object is away from the planet star system, it will exert a mutual gravitational force on it, but they can be neglected. So yes, so they're still there, but they can be neglected. So that's why A is correct. Okay, question 12 is our well-known Atwood machine that we've dealt with before, and it's asking which quantities would allow the acceleration due to gravity in the planet to be determined. And we know there are two ways to solve this problem. The answer gives you the first way. You have to create the you have to consider separate masses as separate systems and make the system of equations and solve for G, right? But you can also consider these two masses and this whole thing as one system and get the same equation. But you know that you need to know the masses of the blocks and the acceleration. So basically this would be the answer. Problem 14, you have to be careful to understand which one's the top, which one's the bottom, right? So this one is the top. This one is the bottom of the circle, and then you just write the equations, the system of equations. So you can solve it in any way that's convenient for you. So what I did, I wrote the second Newton's law for the top, ma equals Fg plus T1 tension, right? So then I found what Fg equals to from this equation, ma minus tension 1, and then I wrote the second Newton's law for the bottom of this of the circle, so ma equals tension 2 minus Fg, and then I just plug in Fg into this equation. So then I just continue my algebra, and then I get 2ma equals T2 plus T1 from this equation, and I find what acceleration equals to. The answer for acceleration is D, tension 1 plus tension 2 divided by 2. Okay, so for question 16, you have a rocket that experiences a force from its thrusters, and it accelerates at 2 meters per second squared upwards. So there are no other upward forces exerted, and wind resistance is negligible. Which of the following combinations of the rocket mass and force from its thrusters would result in an upward acceleration of 2 meters per second? Select two answers. So the answers are A and D. So the key for this problem is to write the net force equation, which is the force of thrusters minus the mg, the gravitational force acting on the rocket, and it equals the mass of the rocket times the acceleration of the rocket. And now you can just plug in the different combinations and see which one would make the correct equation. So the acceleration is 2, you know that you can plug in 2 for acceleration, g is 10, and now you just try different combinations. So mass is 1, you plug in 1 here, and force of thrust is 12. So 12 minus 10 equals 2, it is correct. So A works, B doesn't work, C doesn't work, and D works as well. Problem 18, you have a mass of object M placed on a disk that can rotate. One end of the string is tied to the object, while the other end of the string is held by a pole that's located at the center of the disk. Initially, the object is spun in a horizontal circle of radius r at a constant tangential speed of v0 as shown in the figure, such that the tension in the string is T. At a later time, the disk is spun such that the tangential speed of the object is increased to 2 v0. At a later time, the tangential speed of the object is increased to 3 v0. Which of the following diagrams could represent the forces exerted on the object at one of the given speeds? Assume that the force of state friction is negligible, select to answer. So you have to realize that the tension is the net force and it is the centripetal force. Therefore, when you increase the velocity by the factor of 2, the tension will increase by the factor of 4. And if velocity is increased by the factor of 3, the tension will increase by the factor of 9. This is why A is incorrect, because 2t would not be the correct answer, 3t would not be the correct answer, however 4t and 9t would be the correct answer. In which of the following situations is the gravitational force the dominant force? Select two answers. A and B are the correct answers. So satellite is in orbit around the planet, object is in free fall just after it's released from rest. So electron and proton are bound together, and atom is not, gravitational force is not dominant. And proton and neutron are bound together in atom's nucleus. It's not dominant, and you can see that in situation C, electromagnetic force is the dominant force, and for D, the strong nuclear force is the dominant force. Okay, here's the last problem, number 22. So what we have here, student X ties on one end of a string to a half a kilogram ball and swings the ball in a vertical circle of radius 1 meter as shown in the figure. Student Y uses video analysis to determine the speed of the ball at points A, B, C, and D as shown in the table. That's good job. He uses video analysis. Kudos to him. Student X states that the data is incorrect because the tension in the string provides a centripetal force that should cause the ball to travel with a constant tangential speed. Is student X's reasoning correct? Why not? So at first point you may say yes, student X is correct because it should travel with a constant tangential speed. However, this student X is incorrect in stating that the tension provides the centripetal force, because it's a vertical circle, and tension and combination of tension and gravity provide the centripetal force, not just the tension, right? So it's a little bit tricky question to my opinion, but the correct answer is D. However, I think B would be very tempting to choose. Very tempting would be to choose B, because usually, yes, uniform circular motion assumes during the uniform circular motion we have a constant centripetal acceleration. So that's what we would expect. However, based on this data, you should kind of trust the video analysis, and it's kind of really different. So it's not a random error. It's definitely something's going on here. And yes, so we have to conclude that in this situation, it's not a constant force. It's not uniform. It's not uniform motion, it's not constant acceleration, it's not constant net force. At all points along the ball's path, the force due to gravity from Earth and the force of tension from the string are exerted on the ball. At point A, the ball has the minimum speed and the tension force is at the minimum, since the tension force is the force due to gravity direct over the center. At point C, the ball has the maximum speed even though the tension force is the force due to gravity point in opposite direction. Therefore, the net centripetal force is always changing because it's a combination of the force of tension from the string and the force due to gravity from Earth. As the net centripetal force exerted on the object changes, the tangential speed of the ball changes. Again, it does not apply to the uniform circular motion. Okay, it only applies to the motion. It's still a circular motion, but it's not uniform. Okay, so the tangential speed changes. However, for uniform circular motion, tangential speed stays the same. Therefore, the net force stays the same. All right, that's it.